All right, we're looking at section 3.4, part 4. We're going to be graphing the derivative and the second derivative if we're given the original function. So in this number 1 here, we're given the original function. We're trying to graph the first derivative. So we know the first derivative is based off of the slope. So what I want to do is I want to make an xy chart. So my new y values are going to be whatever the slope is of the first one. So I can just take some points in here. At 0, I can see that slope is very, very steep there. That might be 10. I don't know exactly, but I'm just kind of guessing. When x is 1, I can see the slope isn't quite as steep. Maybe the slope's more like 8 there. When I'm at 2, right here, the slope is 0. When I'm at 3, that slope is the same as it was at 1, but it's negative. When we're at 4, the steep is very slope. Because of the symmetry, I know this would have to be a slope of negative 10. So now when I go to graph f prime, I know at 0 it would be way up there at 10. At 1, I'm going to be way up there at 8. At 2, I'm going to be at 0. At 3, way down here, and at 4, down here. So if I connect those, I can see that I'm getting a line that's decreasing. And what that tells me then, if I look at this line, all of these values are positive. So I should know that from negative infinity until I get to 2, all of the slopes are positive because these values right here are positive. Now this is actually a straight line. It doesn't look very straight. Let me fix that. It should be a nice straight line. And the way that I know that is because this function is y equals negative x squared in some way. Now I can see the vertex is actually 2, 3, so really this function is this. But the big thing I want you to see is this is a parabola that opens down. If I have a parabola that opens down, the derivative would be something like negative 2x. Now I'd actually have to use the chain rule to find this derivative and everything, but can you see how this would be a line that has a negative slope? That's the big thing I want you to see there. Okay, now if I'm trying to graph the second derivative has to do with the concavity of the original function. So if you look at the concavity, here at negative 2, it's concave, or at 0, it's concave down. At 1, it's concave down. 2, concave down. So I know my second derivative has to always be negative for every single x value I check, no matter what it is. So if it always has to be negative, it has to be somewhere down here for the second derivative. I'll do this in red. I don't know exactly where, but it's somewhere, and it has to always have a negative value. And so therefore, this is what my second derivative would look like. So our original function is a line that's decreasing. Is the upside down parabola. Our first derivative is a line that's decreasing. Our second derivative has to be a horizontal line, like this. Also, think about it. If I took the derivative of my first derivative, I would just get a constant. Whatever the slope is of this, that's what my second derivative is. And so therefore, it makes sense that it would have to be just this horizontal line down here. Okay, when we get to number 2, it's a little bit more difficult. But one thing I do know is that this has to be a cubic function, or it'd have to be a fifth, or to the 7th. It's got to be an odd function. So I know the derivative of an odd function is going to have to be an even function. So let's say that I think that this is something like y equals negative x cubed. That's not exactly what it is because it's been shifted up a little bit. It's been shifted up 4. But if you think about finding that derivative, it's going to be something like this. It has to be an upside down parabola. Now, to get a better feel for it, I can do this. I can say, okay, here at negative 3, that slope is obviously negative. Here at negative 2, that slope is obviously 0. Here at 0, the slope is positive something. Here at 1, the slope is 0 again. Actually, this is negative 1, where the slope is 0. And then over here at 2, the slope is something that's negative. So I know that my first derivative is going to have values that are negative, then they have to be 0, then my values are positive, then they're 0, then they're negative. So to make that happen, at -1, I know that I have to have a 0 for my first derivative value. And when x is +1, my first derivative is 0. My values had to be negative for all these x's before this, so my values had to be negative. My value had to be positive at 0. I don't know exactly what it is, but I know it's a positive value, so it's got to be up here. And then my values are 0, and then they're negative. And so that's the way our first derivative is going to have to look. For my second derivative, well, that's based off of the concavity of the original function or the slope of the first derivative. Either one you want to look at. Okay, I'm going to look at concavity. This function is always concave up. So from -infinity until I get to 0, that function is concave up. So the second derivative values must be positive. At 0, at that point, I can see that that's a point of inflection. So my second derivative would have to be 0. From 0 to infinity, my function is concave down, so therefore my second derivative would have to be negative. So graphing that then, I know that from -infinity to 0, I have to have positive values on my second derivative. At 0, I know the values have to be 0. So I have to go from positive to 0 to negative. So it's going to have to look something like that. Straight line. I don't know exactly what it is, but I can support this idea by looking at the second derivative of this function. See how I would get that? It's going to have to be a negative linear function. I don't know if this is exactly the original, but I know it's a negative x to an odd power, probably to the third because of the curvature. So all of this should make sense to you. And that's what you want to be able to do. Based off of the original, be able to graph the first derivative and the second derivative. All right, down here in this next part, we're looking at these clues and we're going to try to sketch the graph. It says f of 3 equals f of 5, which equals 0. So what that's telling us then is that when x is 3, y is 0. When x is 5, y is 0. So I know 2 points. I know this point, I know this point. It says the first derivative is negative when x is less than 4. Well, that tells me, the first derivative tells me slope. So I know from -infinity to 4, my function had to be decreasing. At f prime of 4, it's 0. Okay, I'll think about that in a minute. F prime of x is greater than 0 if x is greater than 4. So from 4 to infinity, if my first derivative is positive, my function had to be increasing. So if my function had to go decreasing to increasing, and right here it's 0, this is going to have to be a minimum, isn't it? And this last clue is saying that the second derivative is positive. Well, that tells me my function's always concave up. So now we're going to put all this together. The function had to be decreasing, increasing, always concave up. So it's going to have to be that kind of parabola right there. That's the only option for it. On example 2, we've got f of 0 is 0, f of 2 is 0. We know those are just points. It says the first derivative is positive if x is less than 1. So from -infinity to 1, our function had to be increasing because it's positive. F prime of 1 does not exist. That can mean a couple of things. That can mean we have a sharp turn, or it could mean a vertical asymptote. We're not sure yet. F prime of x is less than 0 if x is greater than 1. So that means from 1 to infinity, our first derivative is negative, so it's decreasing. Then it says f double prime of x is greater than 0 as long as x is not equal to 1. So what that's telling me is that this is always concave up except at x equals 1. And then the last clue says f of 1 is defined. Well, if f of 1 is defined, then there is not a vertical asymptote there. It has to be a sharp turn. So now the question is, if our function has to go increasing to decreasing, is it just an upside down v if it goes from increase to decrease? Well, it can't be because it's supposed to be concave up. So now I have to draw a function that goes increasing to decreasing. This derivative does not exist, so that's going to mean that it still have to have a max there. So it's going to have to be this kind of a shape to meet all these conditions. Concave up, increasing. At this point there has to be a sharp turn, and then it had to be concave up and decreasing. So the only place where it's not concave up is right there at that cusp. So this kind of a function ends up being this cusp type of graph. Okay? So this one was a parabola, but this one's a cusp because of this right here, that it does not, the first derivative does not exist, so we had a sharp turn. But it couldn't be this one because it does have concavity. This one does not have any concavity, it doesn't have any curvature. Okay?